Hi everyone, I'm Mateusz. I'm software engineer from ScalaUA, and today I would like to talk to you about zio-actors. So for the last few months, I've been involved in contributing to Zio ecosystem, concretely to zio-actors, zio-core, and zio-nio, where for zio-actors, I've completed the actor system functionality, remoting, and first iteration of persistence functionality. And I would like today to share with you about this. So first, let's look into the agenda. So first, I will quickly talk about the concept of actor system. Then just in one slide, I will recall the Akka. And then I will move to zio-actors to show you examples and the library design. And we'll try to spot similarities and differences to Akka. And at the end, I would like to share with you problems you have to face while implementing your own actor system. So let's start. So actor model was first described by Carl Hewitt in his paper from 1970s, where he described it as a set of actors communicating with each other that do not share a common state. And while reading this paper, we can recognize the feature that we're currently using, for example, in Akka, like the idea of work delegation, where we spawn actors and delegate work to them, or interaction patterns like fire and forget interaction pattern. So for the sake of simplicity, let's simplify an actors to such diagram. So for us, actor will receive messages, and then actor will process a message, where within processing, actor can spawn finite amount of children actors and also can send finite amount of messages. And after that, actor can update its behavior, and the whole process starts from the beginning. So that was the general concept. Now let's focus what we would expect from the library design. So for us, actors should definitely have a defined message type. So we should be aware what kind of messages we can send to that actor. Actors should form a supervision trees. So we should be able to define recovery strategies for recovering from errors. And actors should also be location transparent, so we should not be aware whether we're communicating with a remote actor or a local one. So let's quickly, in just one slide, recall Akka. So in Akka, we have the Akka classic, so untyped actors, where we define actors by providing implementation to a receive method. We have also Akka typed, where we model actors processing logic with a behaviors, where within behavior we can define with a type parameter what kind of messages we can send to that actor. And with behaviors, we can update them after processing each message. We have also an actor system for governing over a set of actors. We can spawn an actor, and we can perform interactions with that actor, like fire and forget interaction pattern, or ask interaction pattern. So let's now move to the zio-actors. First, I will also quickly introduce the concept of zio. So zio is an effect type inspired by Haskell I/O monad, where we will model our computations within effects. And here you can see the zio data type, which has 3 type parameters. First type parameter is R, which stands for the environment. So what kind of requirements the effect has to be run, to be executed. Then there is E, which stands for the exceptions. So what kind of failures the effect may fail with. And then there is A, so what kind of result will be produced if effect completes successfully. Of course, using explicitly 3 type parameters all the time would be cumbersome and tedious. So for that purpose, we have multiple type aliases, which I would like to explain because I will use them here extensively. So for example, an effect that has no requirements and can't fail will be a UIO. And for example, an effect that also has no requirements and may fail with a throwable is a task. And there are a few more. Okay, so let's move to the zio-actors. So first we have a constructor for the actor system where we have to provide the actor system name and an optional configuration file if we don't want to use the default application conf from resource directory. And as you can see, this operation returns actor system wrapped into task, so it's wrapped in an effect. Having instantiated actor system, we have access to a few methods. So the first one is make for spawning new actors, where we have to provide the actor name, which should be unique within this actor system, a supervision strategy for recovering from errors, some initial state S, and the stateful, where stateful is basically the description of actor's behavior. And this results in an actor ref, so a reference to an actor. There is also a select method for a local and remote lookup, and a shutdown for stopping the whole actor system. So let's look at this stateful trait. So stateful, as I said, is a description of actor's behavior, and it has 3 type parameters. So first, R is an environment, so what requirements this stateful has. Then S, which stands for the state, and F, which show us what kind of messages we can send to that actor. And when defining our own stateful, all we have to do is provide the implementation for a receive method, where within processing a message, we have access to current actor state, a message that we're currently processing, and the context, where context is basically a handle to the actor system that this actor belongs to. So for spawning children actors and a lookup. And this produces a tuple, SA, where the left-hand side of the tuple is a new state that this actor will be updated with. And the right-hand side is a message that will be sent to a sender in case of ask interaction pattern. So here we are defining what kind of messages will be sent in case of ask interaction pattern on the level of the messages. I will show you it in an example. Then there is an actor ref, so a reference to an actor, where we have access to interaction methods, so question mark, so ask interaction pattern, and the fire and forget, so a question mark. There is also a path, so access to actor's path. So we've seen the general library design. Now let's move to the examples. So the first example will be a simple actor that behaves as a counter. So what we need, first we need to define what kind of messages we can send to that actor. So we need a reset for setting counter's value to 0, increase to increase it by 1, and get to retrieve counter's value. And here in brackets, you can see the type that will have a message that will be sent back in case of ask interaction pattern. So reset and increase are basically expected to be used as a fire and forget, because in case of ask, they will return just the unit. And forget, if we use the ask interaction pattern, we will get the int, so the counter's value. So let's create a new stateful. We're providing the type parameters, and we're providing the implementation for a receive method. So all we have to do is pattern match on the message that we received, where, for example, for reset, we're producing the accordingly a tuple. So for reset, we're setting a state to 0. For increase, we increase it by 1. And forget, we do not change the state. And on the right-hand side, we're returning the state. So let's create such actor. So in a for comprehension, we first create an actor system. Then we spawn a new actor, providing the initial state, so 0, and the handler that we just created. And then we can perform a chain of operations. So we do some increase, we do some get, and then it's taken from a test suite. So at the end, we're checking whether it behaved as we expected. And similarly to Akka, we're here guaranteed with a message ordering between a pair of actors. So now let's move to the next example. So let's build a simple finite state machine with this API. So let's imagine a simple finite state machine that can be either opened or closed. And we have a few transitions. And please notice that this finite state machine is not total because there is no cell transition for a closed state. And for that purpose, we will see how to fail processing a message and trigger supervision strategy. So first let's define the messages. So we want to message open, close, or cell, where for cell we put a string in the brackets because for ask me, we maybe want an invoice or a receipt. Then we create a state trait, so it can be either opened or closed. And for example, a custom case class for an exception for cell message for a closed state. So we create a new stateful, provide type parameters. Here also we have a console for requirement as an environment that will be used here for some simple logging. And all we have to do is provide implementation for a receive method, and this will be as easy as can be. So we basically first pattern match on a state that we're currently in, and then pattern match on a message that we received. So for opened and open message, we do nothing. For a close, so changing a state, we want to perform, for example, some print lining. So it's an effectful put string chained then with producing a tuple. For closed, everything is pretty much the same, except for a cell. So here we can easily fail processing a message with an IO fail, providing some exception. Or what we're currently using. And this will trigger the recovery strategy. So for example, it will rerun processing a message or elevate this to the higher level. So we've seen how to create a simple actors, how to fail processing a message. Now let's look at simple supervision strategy and managing them. So to use a supervision strategy, we need to use the supervisor, and we have a supervisor none, supervisor retry, and supervisor retry with. So here's, for example, a supervisor retry where we provide a schedule that will be executed in case of a message failure. And we plug this policy into the make method that we're executing here. And here we can benefit from a set of comprehensive and composable schedules from Zio. So we have, for example, schedule recurse, schedule exponential, schedule delay, and we can compose them with a logical AND and logical OR. So here's, for example, the S2 is a schedule that will be executed if all the requirements from all the schedules are satisfied. So it will be a schedule that recurs at most 10 times in an exponential manner. There is also a remoting support. Remoting support will be in future used within the clustering functionality. And for remoting, we also require some configuration. So here, configuration we have provided with a Zio config. It's a great library written from scratch with Zio for managing configuration. And configuration for remoting is pretty much the same as in Akka. So we have to provide a host name and port that this actor will be bound to. So let's see a simple example of remoting. So let's imagine that on one node we are creating an actor system, then we are spawning a new actor. And then on another node, we are also creating an actor system and then performing a remote lookup with a select method where we are providing the absolute path to that actor to create a stub. And then we can perform an interaction with this actor ref, just like it would be a remote local one, because we have a location transparency. There is also a persistence. We currently have a first iteration done, so we have a basic persistence functionality together with a one data store support, so a Postgres that is provided by Dubi. And in future, we are going to add the snapshotting and also other data stores. But I would like to show you the API design. So for persistence, we have event source stateful for that purpose, which is based on a default stateful. And it has one additional type parameter, so ev, which stands for the events. And we have also to provide the persistence ID. And here we have two methods. So a source event is a transition from a current state and a given event to the new state. And this function needs to be pure. And there is also a receive method, which is pretty much the same except for a result. So right now, for the left-hand side of a tuple, we have a command that will decide whether to persist an event or not. So for example, command persist or command ignore, and persist with a given event. And the right-hand side is a function from state to the message that will be sent back in case of ask interaction pattern. And this state that we will have access here is the state after performing the source event. So this is a mental equivalent of then run from Akka persistence. So the effect persist and then using then run. So let's see an example of our counter as a persistent actor. So first we need to add additional seal trait counter event that we want to use. So we need the reset event and the increase event. And we also have standard messages, so reset, increase, and get. So we need first to provide the implementation for a source event function. We pattern match on the event that we received and create accordingly a new state 0 or an increment state by 1. Then we also need to provide the implementation for a receive method where we're pattern matching on a message that we received and we're producing accordingly a tuple. So here we're having, for example, the command persist with a reset event, command persist with an increase event, or command ignore if we don't want to perform any persistence. And on the right-hand side, you see that, for example, for increase, we have access to the updated state after performing the source event. And this creates us a whole event source stateful that can be plugged into the actor when spawning. And this actor will use a data store defined in configuration file. So that was all regarding the library design with some examples. Now I would like to share with you the problems you have to face while implementing your own actor system. And while doing this, I was looking a lot at the Akka internals. And the fun part was that one of the source files warned me that I might encounter dragons there. So it was pretty fun. So the first thing I would like to talk about is serialization. So for example, when user defines its own messages, so when it's seal traits, case classes, we can serialize them just like that. The problem arises when the message that user defined contains the part of actor system itself, because we can't just like that serialize actor and then serialize them, because after deserialization, the deserialized actor won't be able to communicate with its original actor system. And for that purpose, we need some kind of duality. So we need within the actor ref, we need the local actor ref and the remote actor ref. So we need an actor to be serialized and deserialized in such way that after deserializing, the actor ref will be able to communicate with its original host, original actor system. And for that purpose, I will show you our first proof of concept implementation with Java serialization. But of course, we have a ticket. We're moving to the other tool for serialization. So first, let's look at the serialization. So the serialized form of an actor is just a path to that actor. So what's sent over the wire is just a string path to that actor. And then there is a deserialization, and when deserialized, we're creating an remote actor ref with a given path. And then when communicating with this remote actor ref, this actor ref will use the socket communication to communicate with its original actor system. Of course, Java is known to be slow and prone to attacks, so we currently have a ticket and moving towards another tool, and this will be a Zio codex, so a separate library within Zio that will provide this functionality. The next thing is a socket handling. So let's imagine that we have multiple actors on multiple nodes communicating with each other, performing fire and forget and the ask interactions. And for that reason, we will have a lot of connections. And we decided to handle them with non-blocking I/O, concretely the Java I/O. With Java I/O, we have a so-called selector mechanism where we can utilize multiple connections with just multiple channels with just one or a few threads. So for example, when in one channel there is, for example, an ask interaction pattern and we're waiting for a message, and then the selector might decide to move the thread from this channel to another one where the data already arrived and we can perform read or write. And we didn't need to implement it with Java I/O API because there is a great Zio I/O wrapper for that purpose. Okay, so to sum it up, I would like to share with you the goals we have for 2020. So we have persistence to be completed. It's currently work in progress. As I said, we have a basic persistence functionality and one data store, so a Postgres, and we're planning to also do the snapshotting. We have a serialization, which is currently also at some point work in progress. We have also metrics, monitoring for the actors also in our backlog. And the last thing that most people ask about and also asked during the functional Scala in London in December when I gave the first version of this presentation. So the clustering, and the clustering will be backed by Zio Keeper, which is currently also work in progress. Okay, so that was all what I wanted to share with you. I think we have still some time for questions. And also, if you have any, please write on our channel on Slack. And thank you very much.
So why you decide not to wrap existing actors, but write their own?
Okay, so basically, so why it's not a wrapper for Akka?
So the question is motivation. Why you don't wrap Akka? Why you write own?
Okay, so basically when I joined the Zio contribution, I was looking for a small project to work on. And I've noticed the zio-actors. It was basically moved from the ScalaZ to Zio organization. And it was basically just this it was just only the one class, like 100 lines of code describing this core actor mechanism, which definitely differs from the Akka. So it was basically just a queue for processing the messages and within these effects, and was just it. And everything what I written, it was based on those decisions. So the actor system, remoting, and so on. And basically, the main idea was to move away from the side effects, like in Akka, sending a message is a side effect, and it's definitely less typed. For example, Akka untyped is definitely less typed. So the main idea was to move even more towards the FP, functional programming. And as I said, here we have a different approach for some things. So as I said, sending a message is not a side effect, it's wrapped in an zio effect. Also, it's fully typed regarding the messages we can send to the actor, regarding the ask pattern, so response messages on the level of a domain that we're defining. So it's just a different approach, and definitely I think it's better to be written from definitely scratch than just a wrapper for Akka.
Okay, thanks. And are you look at an Akka typed?
Akka, yes, sure. Yes, we have also an interop. So interop module for zio-actors and Akka type. So yes, I also spent some time looking at the Akka internals, because, for example, to make some decisions regarding the mechanism inside, I thought that it would be the best to look at the some curated decisions made by Lightband, right? So yes, so it's all Akka is also was a great source for learning. So yes, I also looking at the zio at the Akka typed.
Can you summarize one word the principal difference?
So a difference from Akka?
Yes, principal, yes, the most, no, maybe the most compact.
So as I said, is moving away from sending a message to an actor as a side effect. That's the...
But this is fixed in typed.
So sending a message to an actor, but when you send a message to an actor, it's like you're using exclamation mark, send a message, and it's unit, right?
No, in Akka typed you are. No, in Akka typed you send, you receive other behavior. From the sender side.
But
yes.
The send message is returning unit, like fire and forget, it's just unit, right?
So we come from fire to forget to function, yes?
Yes, so it's basically, yes, moving away from sending a message as a side effect and wrapping it in an effectful way.
Okay, it's clear. Are you plan some analog of persistency? Actor?
So we have a first iteration completed for actors persistency. We are supporting one data store, so is a Postgres, and we have a basic persistent functionality for reading from data store persisting events. We still don't have the snapshotting and other data stores, but the very first iteration, the very first module is already available in the latest version.
Okay, thanks.
So regarding the Java serialization, I said that because we've chosen the Java serialization for a proof of concept, and of course we're currently moving for other tool for serialization. I said it during the talk, and we will be moving for Zio codecs. So there will be also within Zio a separate library for serialization that is meant to be used then in Zio analytics and Zio actors, and also something else, I guess. So yes, so we will be moving away from the just serialization. As I said, is only for a proof of concept.
We will see zio-Kafka.
So there is also zio-Kafka repo. Is a wrapper for, is a connector to Kafka, and it's maintained by Itamar Ravid, and it's also building the Zio analytics. So it's like Apache Flink functionality, but it's also rather on the stage of design sessions and the very first ideas. But so yes, there is a Zio Kafka wrapper. Thank you very much, and have a great Easter.
Have a great Easter. Yeah. Thank you. See you. Bye.
Okay, so bye.